All right, so I welcome you once more to this lesson. We are saying we are doing Math 2200 quiz 1. Okay, so in this quiz, there's section A and section B. Section A uh, contains true or false questions. Okay, so that's the unique thing about Dr. Mbali. He will bring true and false questions in section A. And then in section B, that's where you have your calculations. Okay, that's where you need to solve. But here, section A, you have to answer it based on the understanding that you get, okay, from the notes and from whatever it teaches you. So if you don't read your notes, okay, you will never answer section A correctly. Because you have to read those notes, you have to understand them, and then that's when you can answer these questions. Because all these questions here, okay, on section A, they're just based on the theorems of whatever you learn in class and whatever is in the notes. So please, guys, study the notes, okay? So if I explain anything and you don't understand, you're free to ask. So we'll start from section A there. Okay, so this is section A here, the first 5 questions, okay? So the question is, state with justification, okay? Whether each of the following statements is true or false. Okay. So A, they're saying the trace of any n by m matrix A is found by summing the diagonal entries from A. Okay. So I'll pose this question to you. Do you think this statement is true or is it false? Okay. So the trace of a matrix is only defined for a square matrix. Okay, so the order of that matrix should be n times n, or n times n, I mean, okay, or you can say m times m. In short, the order should be giving us a square matrix. Okay, so the moment you have n multiplied by m, it means here the number of rows and the number of columns are not equal. So this one here is not a square matrix. So we're going to say this statement here on A, we're going to say it's false. Okay, why? Because the trace of a matrix is only valid for a square matrix. But here we see that we do not have a square matrix because we have n and m, meaning that the number of columns and the number of rows are what? Are different. So that is false. Okay, so on A, we're going to say that is false. And then on B, okay, let's read the question. So on B, they're saying given that A and B are symmetric matrices, okay, then A, B transpose is the same as AB. Okay, so do you think this statement is true or is it false? Okay, is this statement true or false? So this is a very important concept that you must get as you are learning the transposes. So what did we say? Okay, we are going. What did we say our transpose is going to be when we get the product of two matrices, according to the notes? Okay, so we're going to say this statement here on B, we're going to say it's false. Okay, so why is it false? Okay, this is because the transpose of the transpose product of two matrices, okay, is not the product of the transposes, okay, but rather it is the commuted um, product of the transposes. Okay, so if I have something like A, B, and then transpose, okay, what I should get here should be B transpose and then A transpose. So the order is like it switches, okay, it commutes. So this one here, if we are applying this transpose to this AB, okay, your answer is not going to be A transpose and then B transpose here. No, okay, it's not going to be that. Your answer should be the commuted product. So you start with the one that is on your right hand side here. Okay, you put the transpose and then you go to the one that is on your left hand side. You also put the transpose. So you always commute the product like that. Okay, but we see here they have not commuted anything. Okay, so we're going to say that statement there is false. Okay, because AB transpose will never be equals to what? To the AB. Instead, it will be equals to BT and then multiplied by A transpose. Okay, so B transpose multiplied by A transpose. Okay, so that's how we answer B. So you can see that you're just applying whatever you learned. So if you don't read your notes, you won't answer. So C, they're saying a square matrix with all its diagonal entries equal to 1 is called the identity matrix. Okay, so is that statement true or is it false? A square matrix with all its diagonal entries equal to 1 is called the identity matrix. Is that true or false? Anyone who can try? Okay, so we're going to say this statement on C here is false. Okay, so it can only be a diagonal matrix if all the entries of the main diagonal are zeros. So we can have a square matrix with all the diagonal entries equal to 1, but that matrix won't be an identity matrix. So for example, if I say matrix A, okay, maybe it has 1, 0, there are 2, and then I have 0, 1, 5, okay, and then here I have 2, 3, 1. Okay, so this matrix here, all the entries in the main diagonal, we can see that they are 1. Okay, but the entries of the diagonal, okay, are not all zeros. So this, we cannot consider this as a square. We cannot consider this as an identity matrix. Okay, no wonder here we're saying false. So it can only be true if all the entries of the main diagonal, okay, are zeros. So you have 0, 0, 0, 0, 0, 0. Okay, so if it's like this, you have your diagonal there, okay, and then of the main diagonal, you can only see 0, 0, 0, 0. That's when the statement of an identity matrix will be true. Okay, but here, the way it was defined here, we are going to say that statement is false. Okay, so if you have any questions, guys, please feel free to ask. All right, what about D? Okay, so D, they're saying the transpose of the sum of two matrices is equal to the sum of their transpose. Okay, so when it comes to the transpose of the sum, okay, it's true. The transpose of the sum is true. So if you have matrix A plus matrix B, okay, and then you apply the transpose there, this is the same as A transpose plus what? B transpose. So this one here is true. So you can even come up with an example if you want. Okay, you can say, okay, let's say this. Let's say, okay, matrix A. Let's just say matrix A is 1, 0, 0, 1. And then matrix B, let's say 0, 1, 1, 0. Okay, so it means A plus B will be what? What will be our A plus B? A plus B will just be 1, 1, 1, 1. Okay, and then let's find the transpose of A plus B. So A plus B transpose, it will still be the same matrix because this row will become a column like that. Okay, so this is the A transpose. What if we find A transpose first? Okay, so A transpose here to be 1, 0, and then 0, 1. Okay, so this one becomes the first row, this one becomes the, this one becomes the first column, this one becomes the second column. So this is our A transpose, and then our B transpose will be a 0, 1, okay, and then 1, 0. So this is what we have. Okay, so when we add A transpose plus B transpose, what we get will also be 1, 1, 1, 1. Okay, so we see that indeed A plus B transpose is the same as A transpose plus B transpose. So the transpose, you can distribute it to the A and B if only you are adding, okay? But remember, we said when you are multiplying, you have to commute it, okay? The first one, the last letter becomes the first one, and then the first one becomes the last one. So always remember that. So we're going to say this one on D is actually true. All right, let's look at E. Okay, so on E, we have this. So on E, they're saying if a matrix A is orthogonal, okay, if the matrix A is orthogonal, then the product of A with its transpose is always the identity matrix. Okay, so is that true or is it false? Okay, is that true or is it false? Anyone who can try. Okay, so in class you learned that if a matrix A is orthogonal, then it means what? Okay, so it means A transpose is just going to be equals to what? To the A inverse. If your matrix is orthogonal. So if here, that's what they are saying. They're saying if A is orthogonal, meaning this, okay, then the product of A with its transpose is always the identity matrix. Yes, okay, we're going to say that is true. Because if A is orthogonal, then the product of A with its transpose, okay, so A multiplied by A transpose, but we see that since this matrix is orthogonal, it means where there's A transpose here, I can put the inverse. Okay, so if this is the same as A multiplied by what? The inverse. So what happens when you multiply a matrix by its inverse? You get the identity. Okay, so this statement here, we're going to say what? It's true. Okay, so you have to learn how to apply the concepts, okay, or the theorems that you learn. All right, we go to question F. F, they're saying the matrix, this matrix that have been given here is not an elementary matrix. Okay, so before you answer here, you have to know what an elementary matrix is. Okay, so an elementary matrix is just a matrix that you get, okay, when you apply only one row operation. Okay, so you have a matrix, then you apply only one row operation, and then you get another matrix. That matrix you're going to call it an elementary what? Matrix. So they are saying this matrix that have been given here, 1, 0, 1, 0, I mean 0, 1, and then 0, 1, 0, and then 1, 0, 0. Okay, they're saying this is not an elementary matrix. Okay, so this statement here is actually false because that guy there is actually an elementary matrix. So what has happened there? There's just been a shift, okay, of the first row with the last row. Okay, so it means the original matrix that we had here was 1, 0, 0, and then we have 0, 1, 0, and then the third one was 0, 0, 1. So it means this was the original matrix that we had. Okay, and then from this original matrix, they applied a row operation where they are switching row 1 with what? Row 3. And then they got this. Okay, so it means this here is an elementary matrix. So this statement that's saying this is not an elementary matrix, we're going to say it's false based on this. Okay, we're going to say it's false, that one. All right, and then we look at G. Okay, so if you have any question, just answer, guys. All right, so G, they're saying an upper triangular matrix is in reduced row echelon form. Okay, an upper triangular matrix is in reduced row echelon form. Okay, so this is not true. Okay, you're going to say this is false. Okay, so an upper triangular, it means every entry below the main diagonal are zeros. That's what an upper triangular matrix is. So for example, I can write 2, 8, 7, okay, 0, 3, 4, and then I say 0, 0, 1. Okay, so this matrix here is an upper triangular matrix. Why? Because it forms a triangle on the upper part. This is a triangle here. No wonder we're saying upper triangular what? Matrix. Okay, but by definition, we say a matrix that has all the entries below the main diagonal to be 0. So this is the main diagonal here. Okay, this is the main diagonal. And we can see that all the entries below it are what? Are zeros. That's what we call an upper triangular matrix. So here they are putting it in general. They're saying an upper triangular matrix is in reduced row echelon form. No, okay, that is false. Because you can just see from this one here, okay, from the matrix that I've drawn here. This matrix here, okay, is not in reduced row echelon form, because the condition for reduced row echelon form, we said all these leading coefficients should be what? Should be 1, and then they should be the only non-zero entry in that column. But we see that those conditions are not being satisfied here. Okay, so no wonder here we're saying false. All right. Let's look at G. Is it H now? H, I mean. So if the coefficients of an unknown, okay, if the coefficient of unknown variables in a system of linear equations, okay, I think you haven't done this, but anyway, if the coefficient of unknown variables in a system of linear equations are put in a matrix form as learned in class, then the system of linear equations has a unique solution if the said matrix is orthogonal. Okay, so this one turns out to be true, but you understand it better once you do um, your system of linear equations. Okay, so but let me try to explain. So whenever the matrix, okay, here they're saying the matrix is orthogonal. So whenever you are told that a matrix is orthogonal, it means that matrix has an inverse. Okay, so we can say whenever the matrix has an inverse, you can simply find a unique solution to your system of linear equations by using the equation, okay, AK is equals to D. Okay, so what we have to do here is just multiply this side by the inverse of A because it's orthogonal, so it has the inverse. Even this side you multiply by the inverse of A. So it means these ones here will just become an identity. Okay, so an identity multiplied by K, it will just be K is equals to, and then here you have the inverse of A and then D. Okay, so this here, okay, make sure that whenever the matrix is orthogonal, or in other words, whenever the matrix has an inverse, okay, you're going to find a unique solution to your system of what? Linear equations. Right, but you understand this better when you do that topic. All right, and then let's look at H. So H there, they're saying what? So we said this one was true. So H, they're saying the following matrix is in reduced row echelon form. Okay, so let's look at this matrix. Is it true or is it false? Okay, so this is false. Why? Because I can see the row of zeros is not at the bottom. Okay, so this one here, it's not at the bottom. Easy. Okay, so this matrix is not in reduced row echelon form. It's not even in row echelon form because the zero rows there are not at the bottom. Okay, we're going to say false. Okay, and then J, okay, this is the last question on the multiple choice. They are saying what on J? Okay, they are saying every diagonal matrix has an inverse. Okay, every diagonal matrix has an inverse. Okay, so is this statement false or true? Okay, we're going to say this statement here is false. Okay, so why are we saying false? We are saying false because the inverse of a diagonal matrix, okay, does not exist for all matrices. Okay, it does not exist for all matrices. Okay, so we said, what is a diagonal matrix? A diagonal matrix is a matrix, okay, that has zeros everywhere apart from the um, okay, not I should not say it like that. A diagonal matrix, okay, is a matrix that has zeros of the main diagonal, okay, but we do not limit what can be in the main diagonal. Okay, so in that main diagonal, we can also have zeros. Okay, but what makes it to be a diagonal matrix is that all the entries of the main diagonal should be zero. Okay, so for example, if I write a 1, a 0, 0, 1, we're going to say this is a diagonal matrix because all the entries of this main diagonal are zeros. Okay, but it doesn't limit the fact that even these same diagonal entries can be zero. So if you write this matrix here, okay, this matrix here, we're also going to say it's a diagonal matrix. Why? Because all the elements of the main diagonal are what? Are zeros. Okay, so if for example, I get this matrix, okay, I've proved that this matrix here is diagonal because all the entries of the main diagonal are zeros. Why? Okay, so does this matrix here have an inverse? Okay, it does not have because this will be 0 minus 0. Okay, so the determinant here will be 0, and we know that we need the determinant when we're finding the inverse, right? Okay, so if the determinant is 0, it means we can't find the inverse of that matrix. So it means this statement here is false based on this reasoning here. All right, so any questions there before we go to section B? All right. Section B now. Okay, so there's question 2 and question 3, but I won't solve question 3 because you haven't yet done the system of linear equations. So I'll just solve this question here and then we'll call it a day. So they're saying solve each of the following questions. A, given a matrix A with trace minus 2, find the trace of 4 multiplied by A transpose. All right, so here you have to know some certain property. Okay, so what you need to know here is that the trace of a matrix A is the same as the trace of the transpose of A. Okay, so if you get the transpose of a certain matrix, the trace does not change. Why? Because the entries that will sit in the main diagonal when you find the transpose won't change. So for example, if this is my matrix A, I have 2, 3, 4, 5, right? Okay, and then I find my A transpose to be 2, 3, 4, 5. So you see that these entries here in the main diagonal, they are not changing even if you have found your A transpose. And we know that the trace is just the sum of all the elements that sit in the main diagonal, right? Okay, so it means here, okay, here where there is AT here, okay, I can put the trace of the matrix A. So here I've been given that the trace of A is what? Minus 2. So this one here, I'll factorize the 4. So this 4 will go outside. So I'll remain with 4. And then I'll have trace of A transpose. So this is going to be equals to 4. Okay. So what is the trace of A transpose? Okay. The trace of A transpose is the same as the trace of A. Okay. So I'm just going to multiply by minus 2. This will give me what? Minus 8. All right. So that's how we answer the first question there on number 2. All right, let's look at B. So B, they're saying, let A be an invariable matrix such that A to the power 3 minus 3A squared plus A is equals to 0. Then show that the identity matrix is just going to be equals to 3A minus A squared. So this is a question from the tutorial sheet. Okay, so another thing is that all these questions now that we are going to solve here below are all from the tutorial sheets. So if you don't solve your tutorial sheets, you'll be doomed. So solve those tutorial sheets for Math 2200, okay? And then read the notes, then you'll be good to go. All right, so let's prove that this guy is actually this guy, okay? So the proof is not even hard there. So let's write what we have. The power 3 minus the power 2 plus A is equals to 0. So I must mention that if I have the inverse of A multiplying my A, this is the same as the identity. And it's the same as A and then the inverse of A. Okay? This is the same. So whenever we have this situation, we're just going to be replacing with the inverse, the identity, I mean. All right, so now let's look at this question. So I'll write this as A, and then A, because it's A to the power 3 minus 3, A plus A is equals to 0. Okay, and then from there, I'm going to multiply. Okay, throughout, I'm going to multiply by A inverse. So if I multiply by A inverse here, I'll get A inverse with one of these A's. Okay, and then I have A, then minus 3. Okay, the A inverse goes to this one here. So it will be A inverse, and then A, and then I also have A, and then plus. If it multiplies this, it is just A inverse A is equals to 0. Okay, from there, what are we going to have? So let's erase what we have on top. So from there, we see that this here is just going to be an identity. So we have an identity multiplied by AA to just be AA. Minus C, this will be an identity. So it will be 3 multiplied by an identity multiplied by A. That will be 3A. Then this one will just be plus identity. Okay, and then is equals to 0. And then from here, we can just make I the subject. So it will be I is equals to this AA is just A squared. Okay, and then this minus 3A goes to the other side, becomes positive 3A, and then minus A squared. So we've seen that we've proved from this, we are now there. Okay, so you say hence proved. All right, so any questions there? right, no question. Let's look at C. Okay, so C, they're saying show that if B is a square matrix, then B minus B transpose is a skew symmetric what? Matrix. Okay, so what are we going to do there? Okay, so we know that if B, okay, let me just use another term. Okay, so we know that if A is a skew symmetric matrix, symmetric, okay, then it means that A transpose will just be equals to minus what? A. That's what the definition says. If A is a what? Skew symmetric. So if you want to prove that this guy here is skew symmetric, then we have to show that B minus B T transpose is just the same as minus B minus B T. Okay, we have to show this. That's all. Okay, based on this definition here. If this is skew symmetric, we have to show this relationship here. Okay, so what are we going to do? Okay, we are going to say let P be equals to B minus BT. Okay, and then this will mean that what? Okay, this will mean that if I have minus P, that will just be minus, and then I have B minus BT, right? You agree with me? So I've just multiplied the minus here and the minus there. I have that. Okay, and then if I get this guy, okay, I say P is equals to B minus BT, and then I apply transpose here. Even here, I apply transpose. Okay, what am I going to get? So P transpose will just be P transpose is equals to, and then here, okay, remember we said the transpose can be distributed when you are adding. Okay, so even when you are subtracting, can also be distributed. So we're going to say this transpose to the B to be B transpose, and then minus B transpose with another transpose. It's just going to cancel. So you're just going to have B. Okay. And then from there, what do? We factorize the minus 1 from here. So what we have currently is that PT, which is P transpose, is equals to, and then we have, okay, from here I'm going to factorize a minus 1. So if I factorize a minus 1, what am I going to remain with? Okay, if I factorize a minus 1, what am I going to remain with? I'm going to remain with minus BT and then plus what? B. So this will mean PT is equals to, and then this will be minus, okay? This will be minus, and then what we have here is just what? B minus BT. All right, so we see that we set our P to be equals to this, and then our P transpose, okay? Our P transpose is just the negative of the same thing that we had, okay? So we see that P transpose is equals to minus B minus B transpose, and then the P is equals to this. So it means this condition here has been what? Satisfied, okay? Because here we can write that, okay? Here we can write that, let me write here, okay? Here, from here, we can write that P transpose is actually equals to minus, okay? Remember, we had set B minus B transpose to be P. Okay, so if this here is achieved, then we have proved that it is a what? Skew symmetric. All right, so we're going to say hence proved. So that's how you do the proof there. Okay, D, let's look at D. Okay, so on D, they're saying show that the matrix A is orthogonal. This is coming from the tutorial sheet. Okay, this is coming from the what? From the tutorial sheet. So if it's orthogonal, we just have to show that A transpose is actually equal to what? The A inverse. Okay, so if you want, you can find the transpose and then you show that it is equal to the what? To the A inverse. So you find the A transpose first and then you find the A inverse. Okay, if they are equal, then we have proved. But if you want, you can use this one. So since AT is equals to the inverse, okay, so it means when I multiply this AT with the A, what should I get? I should get the identity matrix. Okay, because this AT or A transpose is the same as the inverse. So if I multiply them, I should get the what? The identity. So let's find the AT there. Okay, so I'm going to say A multiplied by AT is equals to A is just cos theta sine theta. Here it's minus sine theta, cos theta. Okay, and then let's find the transpose. So the transpose is this row becomes the column. So we have cos theta sine theta. Okay, and then this here is another row. So it becomes the second column. So it is minus sine theta and then cos. Okay, so that is what we have. And then let's try to multiply this. So this multiplied by this is going to give me what? Cos squared theta. This multiplied by this, it will be plus sine squared theta. Okay, this multiplied by that, it will be minus cos sine theta. Okay, and then this multiplied by that to be plus sine theta cos theta. Okay, and then this multiplied by this, it will be minus cos theta sine theta plus, okay, this multiplied by this, it will be cos theta. Yeah, what did I write squared? So cos theta sine theta. Okay, and then now this multiplied by that, it will be sine squared theta plus this multiplied by this, it will be cos squared theta. So we see that this what we have is just an it's just an identity matrix, right? Because from the identities, we know that sine squared theta plus cos squared theta is what? Is 1. Okay, so we're going to say this is 1. These here are the same and they have different signs, so that is 0. Even here is 0. Then there it's what? It's 1. Okay, so it means we have shown here that indeed this matrix A is an orthogonal because when we get its transpose, we multiply it by A, okay, we're finding the identity. So it means this transpose is actually equals to what? To the inverse, okay? So sometimes use um, use this method because it's easier. Okay, sometimes it will be very hard for you to find the inverse. Okay, because here we are just given a simple matrix. Okay, so you can easily find the inverse here. But what if you are given a 4 by 4 matrix? Okay, how are you going to find the inverse? So just find the transpose, multiply. If it gives you the identity, you say it's orthogonal. If it does not give you the identity, it's not orthogonal. So that's a shortcut you can use there. All right, so any questions, guys, there? Okay, let's solve the last question then for today. Okay, so the last question they're saying find the values of x for which the matrix, okay, that matrix that we have been given there is not invertible. Okay, so what does it mean not invertible? Okay, so not invertible, it means it does not have an inverse. Okay, so does not have an inverse simply also means that the determinant is what? Okay, the determinant is 0. Okay,
So is
all
it
right.
not invertible or is invertible?
Oh, what did I read? I read not invertible.
Yes.
Oh, okay, I've made a mistake. So they are saying find the values of x for which this matrix is invertible. Oh, okay, yeah. So it means we have to find the values of x, okay, such that when we put that value of x there, okay, the matrix will have an inverse. Okay, that's what it means to be invertible. It has an inverse. All right, so it means here what we have to do, okay, we can solve it in 2 ways. So here we have to make sure that the determinant is never 0, because once the determinant becomes 0, then that matrix will not be invertible. So our goal here for us to find those values of x is to make sure that the the determinant is never 0. So this is a 2 by 2 matrix. So how do we find the determinant? Okay, we're going to say this guy multiplied by 2, x squared plus 1 Okay, then minus what you have in the minor diagonal, which will just be 0. Okay, so this gives us a determinant. Okay, so we're going to say this determinant should never be equals to what? To 0. So this is the first way in which you can solve it. Okay, so what you're going to do here to just be 2x squared plus 2 should not be equals to 0. And then it will be 2x squared should not be equals to minus 2. And then divide by 2, it means that x squared should never be equals to minus 1. Okay, so as long as this condition here is satisfied, then it means that um, the matrix that you're going to have, okay, is going to be what? Invertible. So the way you can represent your final answer here, you can say the x values, okay, let me write it like this. You can say the x values, okay, should be such that x is a real number, okay, but maybe here we can try to find the square roots. Okay, so we can square root this side, square root that side. We're going to have x should never be equals to plus or minus the root of minus 1. So the root of minus 1 is what? The root of minus 1 is it I? Your complex numbers, like that. Yeah. So x should not be equal to plus or minus I there. Okay. So x should not be equal to plus or minus I. So you can get any value of x as long as it's not equal to this, then it will make this matrix here to be invertible. Okay. But the moment your x equals to the plus I or the minus I, then that matrix becomes not invertible. Okay. Because you won't find the inverse there. All right. So this here will be the set of the x values that we are going to need for this matrix to be what? Invertible. Right, so I'll end there unless there are other questions. All right, so have a blessed night. I'll share the recording as well.